Image. This illustration depicts the merger of two neutron stars. The rippling spacetime grid represents gravitational waves that travel out from the collision, while the narrow beams show the burst of view. More credit National Science Foundation, Lagos State University. Simone on August 17, 2017, at 124,104 UTC, scientists made the first direct observation of a merger between two neutron stars, the dense, collapsed cores that remain after large stars die in a supernova explosion. The merger is the first cosmological event observed in both gravitational waves, ripples in the fabric of spacetime, and the entire spectrum of light, from gamma rays to radio waves. University of Maryland researchers played key roles in detecting both the gravitational and light signals of the historic event. UMD scientists co-authored several research papers published on October 16, 2017, including two that describe major aspects of the discovery: the gravitational wave observations published in the journal Physical Review Letters and the X-ray observations published in the journal Nature. Gravitational waves from the event, named GW170817, arrived first at the Twin Laser Interferometer Gravitational Wave Observatory LIGO detectors, located in Hanford, Washington, and Livingston, Louisiana. Because of the orientation of the neutron star pair, the newly operational Virgo detector, located near Pisa, Italy, observed a weaker signal. Less than 2 seconds later, the gamma-ray burst monitor on NASA's Fermi Gamma Ray Space Telescope detected a short burst of gamma rays. A rapid analysis of these signals enabled the LIGO Scientific Collaboration LSC and the Virgo collaboration to locate the signal in a region covering less than 0.1% of the total sky area as viewed from Earth. Fermi independently identified a larger area consistent with that identified by LIGO and Virgo. Astronomers around the globe then directed more than 70 space and ground-based telescopes toward the event for follow-up observations. "This is the most intensely observed astronomical event in history," said Peter Shawin, a professor of physics at UMD and an LSC principal investigator who serves as Data Analysis Committee chair for the LSC. Shawin and his students led the effort to develop protocols to alert astronomers in the event of a neutron star merger or any other gravitational wave event that could be observable by electromagnetic telescopes. LIGO was built with binary neutron star mergers in mind, said Shawin, who is also a fellow at the Joint Space Science Institute. Detecting binary black hole mergers first was a treat, and we've learned a lot from them. But the fantastic thing here is the astronomy discoveries that followed the gravitational wave signal. It's just what theorists have predicted we should see from such a system, and we're seeing it across the entire light spectrum. The neutron stars merged in a galaxy called NGC 4993, located about 130 million light-years from Earth in the constellation Hydra. Prior to the merger, each of the two neutron stars was slightly more massive than the Sun. But the neutron stars were also extremely dense, each jammed into a sphere with a diameter roughly equal to the width of Washington, D.C. As the dense neutron stars spiraled together, the pair emitted gravitational waves that were detectable for about 100 seconds. Their collision produced the gamma-ray burst detected by the Fermi Space Telescope about 2 seconds later. For the binary black hole mergers LIGO has already observed, the signals were much shorter, just a fraction of a second, said Alessandra Buonanno, a UMD College Park professor of physics and LSC principal investigator who also has an appointment as director at the Max Planck Institute for Gravitational Physics, in Potsdam, Germany. "We were able to track the evolution of GW170817 over time in a way we could not achieve for two black holes. As we continue to examine the signal, this wealth of data will likely allow us to pursue new and more stringent gravitational tests which could put Einstein's theory of general relativity in question." Buonanno leads an effort to develop highly accurate models of gravitational waves that neutron stars would generate in the process of orbiting around each other and eventually colliding. While analyzing GW170817, Buonanno's team and other members of the LIGO and Virgo collaborations used these waveform models to identify the signal source as a pair of orbiting neutron stars about to merge. The waveform model that corresponds to this signal helped us determine that the two bodies each had a mass between 1 and 2 times that of the Sun, Buonanno added. "This is the mass range we would expect from neutron stars. Unlike what we would expect with two black holes, we saw a strong counterpart to the gravitational wave signal in light and other radiation. This gives us a first look inside a neutron star and an opportunity to probe its composition." In the days and weeks following the gravitational wave signal and the gamma-ray burst, astronomers captured other forms of light: X-rays, ultraviolet, optical and infrared light, and radio waves. Each observation revealed new discoveries or opened new doors to further research questions. With the Fermi detection of the gamma-ray burst, everyone was already excited. A few hours later, we saw the transient for the first time, said Eleonora Troja, an assistant research scientist in the UMD Department of Astronomy and lead author of the Nature paper that describes results from NASA's Chandra X-ray Observatory and the Hubble Space Telescope. A transient is a general term for any short-lived astronomical phenomenon. For an astronomer, this is a wonderland. Every other day I was in awe, thinking it can't get better than this. Then something new came along, said Troja, who is also a member of the Swift Gamma-ray Burst mission team at NASA's Goddard Space Flight Center. Within a few days, we realized we were seeing a rare transient called a kilonova in more detail than ever before. Astronomers believe that the decay of radioactive elements formed in neutron debris creates a kilonova visible in infrared light. Troja and her co-authors were one of the few groups to make detailed observations of this infrared light. Based on their data, the team estimated that the kilonova created a truly staggering amount of platinum and gold, with a combined mass several hundred times the mass of Earth. The results suggest that colliding neutron stars may be the universe's dominant source of heavy elements. But the kilonova was not the last discovery to be made. 9 days later, the X-ray emission started to show up, Troja continued. I was the first person to see it, and I couldn't believe my eyes. We were seeing a phenomenon called an orphan afterglow. An orphan afterglow is a transient phenomenon, predicted by theory but not conclusively observed until now, which originates from a gamma-ray burst but is visible for days or even months after the event. For nearly 2 decades, astronomers have searched for traces of an orphan afterglow to help explain the enigmatic origins of gamma-ray bursts. According to Troja, the afterglow seen following this event suggests that the neutron star merger launched astronomical jets that are slightly off-axis, or in other words, not pointed directly toward Earth. These jets, in turn, most likely powered the short gamma-ray burst observed by the Fermi telescope. Nearly every gamma-ray burst we have observed so far has been pointed directly toward Earth. Picture the beam from a flashlight. If the telescope doesn't look down the axis of the jet, we don't see the signal, said Sylvain Vallot, a professor of astronomy at UMD and a co-author of the Nature paper. For this event, picture the stream of water from a garden hose. Instead, the central jet moves very fast, but there is also a cone of radiation that sprays out from the sides. The 9-day delay in signals confirmed that we were seeing the event off-axis, added Vallot, who is also a fellow at the Joint Space Science Institute. We have likely missed a large fraction of these off-axis events because they are over so quickly and we haven't known where to make follow-up observations. But with successful coordination between the LIGO network and electromagnetic telescopes around the world, it's likely we'll see many more. Theorists have predicted that when neutron stars collide, they should give off gravitational waves and gamma rays, along with powerful jets that emit light across the electromagnetic spectrum. The new observations confirm that at least some short gamma-ray bursts are generated by the merging of neutron stars, something that was only theorized before. For decades we've suspected short gamma-ray bursts were powered by neutron star mergers, said Julie McHenry, Fermi project scientist at NASA's Goddard Space Flight Center, adjunct associate professor of physics at UMD and a fellow at the Joint Space Science Institute. Now, with the incredible data from LIGO and Virgo for this event, we have the answer. The gravitational waves tell us that the merging objects had masses consistent with neutron stars, and the flash of gamma rays tells us that the objects are unlikely to be black holes, since a collision of black holes is not expected to give off light. But while one mystery appears to be solved, new mysteries have emerged. The observed short gamma-ray burst was one of the closest to Earth seen so far, yet it was surprisingly weak for its distance. Scientists are beginning to propose models for why this might be, McHenry said, adding that new insights are likely to arise for years to come. While the results from this event are beyond my wildest dreams, the most exciting part is that this is really just the beginning, said Brad Schenko, principal investigator of the Swift Gamma-ray Burst mission at NASA's Goddard Space Flight Center, adjunct assistant professor of astronomy at UMD and a fellow at the Joint Space Science Institute. Schenko is also a co-author of the Nature paper. LIGO and Virgo are offline for upgrades now, but in 2018 they will start observing again with even greater sensitivity. With such amazing data across the electromagnetic spectrum from just this first neutron star merger, a new era of multi-messenger astronomy is truly upon us. The research paper, GW170817 Observation of Gravitational Waves from a Binary Neutron Star in Spiral, by the LIGO Scientific Collaboration and the Virgo Collaboration, was published in the journal Physical Review Letters on October 16, 2017. The research paper, the X-ray counterpart to the gravitational wave event GW170817, Eleonora Troja et al., was published in the journal Nature on October 16, 2017. In addition to Troja, Velo, and Shanko, the Nature paper is also co-authored by Alexander Kutarev, an associate research scientist in the UMD Department of Astronomy. Other related research papers co-authored by UMD-affiliated scientists include Illuminating Gravitational Waves, a concordant picture of photons from a neutron star merger, Kasliwal et al., published online in the journal Science on October 16, 2017. UMD-affiliated co-authors: Shanko and astronomy postdoctoral researcher Leo Singer. Swift and New Star Observations of GW170817 Detection of a Blue Kilonova, P.A. Evans et al., published online in the journal Science on October 16, 2017. UMD-affiliated co-authors Shanko and Troja. About LIGO and Virgo. LIGO is funded by the National Science Foundation (NSF) and operated by Caltech and MIT, which conceived of LIGO and led the initial and advanced LIGO projects. Financial support for the Advanced LIGO project was led by the NSF with Germany Max Planck Society, the UK Science and Technology Facilities Council and Australian Research Council making significant commitments and contributions to the project. More than 1,200 scientists and some 100 institutions from around the world participate in the effort through the LIGO Scientific Collaboration, which includes the GEO Collaboration and the Australian Collaboration OSGRAV. Additional partners are listed at http://ligo.org partners.php. The Virgo collaboration consists of more than 280 physicists and engineers belonging to 20 different European research groups, 6 from Centre National de la Recherche Scientifique CNRS in France, 8 from the Istituto Nazionale di Fisica Nucleare INFN in Italy, 2 in the Netherlands with NICEF, the MTA Wigner RCP in Hungary, the POLGRAW group in Poland, Spain with the University of Valencia and the European Gravitational Observatory, EGO, the laboratory hosting the Virgo detector near Pisa in Italy, funded by CNRS, INFN, and NICEF. Media Relations Contact Matthew Wright 3,014,059,267, me Wright at umd.edu University of Maryland College of Computer, Mathematical, and Natural Sciences 2300 Simons Hall College Park, MD 20742 http://www.cmns.umd.edu at UMD Science.